Now, this is not quite the whole story, right? Because, I mean, these VR1s and VR2s, we don't really know what they are yet. So what do we do now?
Well, we have a second law, right? We have KCL, or the current law.
KCL.
Let's talk about currents.
Okay. Well, let's see. So maybe I should label, because I know about Ohm's law, maybe I'm going to naively label an I1 that goes through the first resistor and an I2 that goes to the second resistor. And notice that I pick these so that they match the direction of Ohm's law. That's just for convenience, right? These are unknown at the moment. I don't know if they're going to be plus or minus. So what does KCL tell me, though?
Well, now that we've labeled the currents in the circuit, let's find a node that those circuits go in or those currents go in and out of.
Yeah, how about this one?
Yeah, that center node looks good.
And so you want to write KCL here?
Yeah.
Okay, so provided nothing's connected to this terminal, which it isn't, then what does KCL tell me? It's pretty trivial, but what is it?
Yeah, the current entering the node is equal to the current exiting the node.
Okay,
so I1 is entering, and it's equal to I2.
Okay, so it tells us something that many of you, realized when you were just staring at this, which is there's only one current going down, and around the whole circle, the whole loop. And for convenience, let's just call this I. We don't have to keep calling them I1 and I2. There's just one current that goes through the battery, and it also goes through the resistors. Actually, there's one, let me correct that. There's one current that goes through resistor 1 and one current that goes through resistor 2.
That's right.
Okay, so fair enough. Now, how do we want to put this together? Well, we can use Ohm's law now. Okay, so if I do 1 and really 2 is kind of implicit, and I add Ohm's law to this, right? What are we going to get? Well, we're going to get the following: minus Vn plus, and now by Ohm's law, we know that the voltage across the resistor is the current I times its resistance, and that's R1, and I times R2, and that must equal 0, and I'll rewrite that as Vn equals I times R1 plus R2, or the one we're going to use is the same equation, just solved for I, and that's Vin R1 plus R2. Now, this is great. This is a great result. Now we know the current going down these resistors because we know this, right, given, and we're also given these two resistor values. Okay, great. Now we can solve for that. But is that what we wanted exactly?
No, but I think we're pretty close. I mean,
Okay.
we're interested in that central node because that's connected to the output.
Okay, so how about we figure out the voltage of that central node relative to this, sort of ground that you pick, this sort of baseline, sort of ground level, so to speak. If we do that, then we already have that kind of, right? Because that's VR2, right? Exactly how high is this over, above this level? So what we want here, the voltage between this point and here is VR2. If we write VR2, we know that must be I times R2. Well, we happen to know I, we just solved for it, and here we get the result we were hoping for, okay? And it took us a little bit, but it was worth the wait. Oops, let's make that a 2, there we go, and that's V in. Okay, so now notice a couple of things. First off, the voltage across a given resistor in a resistive divider is the ratio of that resistor to the total resistance. All right? And that's a common motif. That only works, however, for resistors that are in series. In other words, they're one after the other. They're along the same branch, one after the other, and there's nothing connecting in between them. So in other words, if I have two resistors, okay, and I know the voltage between here and here, and I call that Vn, then I know the voltage across any one of these resistors, provided there's nothing connected here. Right? We don't want anything connected off the resistor because that messes this up. I could easily solve for the voltage across VR1, and that's just I times R1. So it'll be the same expression, but there'll be an R1 up here. So it's the ratio of that resistor to the total.
So it looks like the two resistors are distributing that total voltage amongst themselves.
So if you have a bigger, if R2 is bigger than R1, then this number would be bigger, and so that fraction would grow. Okay, so this is 1/2. So now what we want to do is put this together with the second half and then kind of come up with the whole use for the voltage divider and kind of explain to you why we would do a Wheatstone bridge. Okay, so now we've got our second loop, and the analysis of this is...
It looks like it's almost identical, just the resistor values have
That's
changed.
right. So the expression will be the same. You'll still have only one current I, and you'll have to label your resistor voltages. Okay, so we'll go ahead and label them in the same way we did before. Okay? And we'd like to solve for the voltage between this node here and that point there, which is shared, of course, by this and the branch we just did a moment ago. So I think this is a very good practice problem for you to try, just to kind of go through the motions of doing it. Okay, so applying the same logic we did before without going through the whole thing, this voltage divider will tell us that the voltage at this point, VR4, okay, voltage between this point and this bottom thing is R4 divided by R3 plus R4, once again, times Vn. Okay, well that's good. Now we know the voltage of this point with respect to the ground. It's not really formally ground, but to this sort of bottom node. And the voltage, the VR2 voltage we solved one slide ago. So let's put that together.